Well, you probably had some idea that with all the talk about stratosphere and ozone and so on, we are headed towards the first idea about geoengineering, which is to try to reduce solar radiation by sprinkling dust in the stratosphere. So nature provides us some experiments on this with volcanic eruptions. There are lots of details because it depends on where the volcano is. You remember the tropopause drops off to lower altitudes as we head towards the poles because the temperatures are colder, atmosphere is thinner, denser, and so on. So higher latitude volcanoes can more easily reach into the stratosphere. Stratosphere has unique stratification, which is why we call it stratosphere, and it doesn't have much weather, so it's cold compared to the tropopause as well. As you remember, tropopause gets cold and stratosphere starts from the tropopause, so it has very little water and so on, and it has some unique chemistry that if you put stuff in it, they can stay there for a long time. So one of the more recent giant explosions, volcanic eruptions, was Pinatubo in June of 1990. I think we will see some data and so on. Fortunately, it gave lots of signals, and there were warnings issued by the USGS, US Geological Survey. There were evacuations done, so loss of life was reduced, and it put enormous amount of ash, rocks, chemicals, aerosols, all sorts of things. And here is a nice photo of a wall of ash following this little truck trying to run away. So in some places the thickness of the deposition of ash was almost 200 meters, and you can see it covered everything and crashed roofs and so on and so forth. The idea is to figure out exactly what happens when such a volcanic eruption happens when it goes off, so that we know what we are in for if we decide to do solar radiation management using using methods of putting aerosols into the stratosphere. This is satellite data from Earth Observatory of NASA showing certain spectrum of optical depth at 1020 nanometers before the volcanic eruption, April 91. So it was June 91, not 1990, the eruption. 91 April 10 to 91 May 13, and you can see that the eruption happened around June 10, 11, and so on for a few days. As soon as the eruption went off, few days later, 91 June 15 to 91 July 15, you can see tremendous global changes in the tropics as well as in some high latitudes. So the Pinatubo, which is located on Luzon Island in the Philippines over here in the northwestern Pacific, is very much a tropical island. So the tropical circulation picked it up and moved it around fairly quickly with the dynamic patterns that we are used to in terms of tropical extratropical connections, which you can look up in my course on tropical dynamics. Okay, so this is for 91 August 23 to 91 September 30. You can see the spreading into both hemispheres, and by December of 93 into January of 2016, the peaks have been smoothed out, and then you're beginning to get patterns. So the main thing to notice is that there are dynamics which spread things around. In a zonal direction, there are strong upper level winds, and there is meridional circulation in the stratosphere as well, which is related to the ozone circulation, for example, the so-called Dobson-Brewer circulation, and so on and so forth. So you do expect the tropical injection of aerosols to spread meridionally and eventually get rained out through various processes. but the lifetime of aerosols in the troposphere, in the stratosphere, is much longer than it would be in the troposphere, where you have a lot of weather and deposition can be much faster and the washout can be much faster. Going to some Greenland ice core data, looking at past eruptions. This is looking at depths of the ice core and sulfate concentration. So one of the major aerosols coming out of the volcanoes are the the sulfates, which require a little bit of moisture to become very scattering and reflective. So the stratosphere does manage to keep that much moisture from volcanic eruption. So here is the 1810 AD eruption seen as a peak in sulfate aerosol. I think Tambora was in, or was it Krakatoa, in 1815, and 1820 had another small one, and this one is from 1883, I think. Let me look it up quickly. I should remember these. 1880. Come on. Why is it behaving funny with me? So Krakatoa was 1883, and 1815 must have been Tambora. Oops, sorry. Why did I jump? Okay. So Edvard Munch, you know, as aerosols are put into the atmosphere by the volcano, the sunsets get very colorful. So this is from Edvard Munch. I think he may have done this from Asylum. But anyway, this is quite a famous one, and he had a secret message typed on it somewhere, which is being discussed recently. So depending on the amount of aerosols put in, the effects will last for multiple years, as we will see in a minute. There are lots of anecdotal stories about how the 1815 Tambora ended up creating the 1816 year without summer, and how the crops failed, and then Mary Shelley and the other person who wrote Dracula all went off to write horror stories because of the dark summer and so on and so forth. But some research argues that these temperature anomalies in 1816 and Mary Shelley's Frankenstein and so on are not really related to Tambora, but nonetheless we will see that volcanoes do have a huge impact on the radiation budget, on various other factors. This is from the Past Global Changes or PAGES program, which did some modeling for the 1815 Tambora eruption, and also used tree rings to see there were missing tree rings. Tree rings are basically recording summer temperatures and rainfalls. The thickness of the trees, the width of the tree rings, sorry, are related to the seasonal changes in temperature and precipitation. Roseanne D'Origo and others, Ed Cook and so on from Columbia University, work diligently on these things. So the modeling basically shows that you get a kind of complicated pattern of global anomalies. These stippled regions are where most of the models agree, and you can see there are a lot of regions where they don't agree, but nonetheless, whenever you put in aerosols into the stratosphere, it tends to move it to the polar regions. You have polar stratospheric clouds, and clouds offer nuclei on which some special reactions happen, like destruction of ozone by CFCs and the aerosols, some of the aerosols in the volcanic eruptions, and that's why you end up with ozone holes at in the southern hemisphere or Antarctica, for example. But the radiative forcing of the Arctic Circle also ends up creating perturbations to the jet stream, which can create these kinds of warm cold kind of patterns, the wavy pattern you typically see in the jet stream, and so on. Okay. Maybe I will leave this here and then continue in the next podcast, but the main thing is, if we are going to do geoengineering, which involves spraying stuff in the stratosphere, then we should know all the perturbations that happen because of it, how long they last, how damaging they can be, other than the main purpose of geoengineering, which is to just reflect sunlight. But there is no free lunch, so it comes with all sorts of perturbations to the tropospheric climate, and unintended consequences have to be very clearly understood. That's the purpose of looking at Pinatubo as a natural experiment, and then combine with other volcanoes and models to understand the cascade of events that happen once a volcanic eruption occurs.